power series, and in this lesson we get to its applications and operations. Now you may be wondering, well, why power series? As we go through this video, you'll realize that there will be certain instances in calculus where you have no option but to revert to reducing a particular function to a series of powers of x. So it is important that you get and obtain the correct series for that particular function. So our first application is differentiation. Well, what do we mean by that? How do we differentiate? Well, looking at this particular example, is sine of x, which is the standard series, x minus x cubed over 3 factorial, and so on. We want to find the first 4 non-zero terms of the expansion for cos 3 of x. Now, what we could possibly do is use a Maclaurin series to find the expansion for cos 3 of x. Now that in itself would be correct. However, the aim here is for you to realize that differentiation can be applied to a power series. So let's do that. And how do I go about finding the expansion for cos 3x? Well, there's your series for sine of x. Let us differentiate the series sine of x. Therefore, my derivative of sine of x, which is that, if I differentiate the left-hand side, I must differentiate the right-hand side. So it will be the derivative of x minus x cubed over 3 factorial, x to the power 5 over 5 factorial, each one of those terms differentiated. Well, we know what the derivative of sine x is. The derivative of sine x is cos of x. And we know exactly how to differentiate a simple term containing x. So what is my derivative of x? That is 1. What is the derivative of x cubed? 3x squared. Now I'm going to do something, and that is to show you how I get the final answer. What does 3 factorial mean? 3 factorial in the denominator means 3 times 2 times 1. And you'll see why I have done it that way. You don't need to do this because I'm pretty sure you can see the answer quite easily. But in my explanation, I'm going to expand the factorial notation. So let's go on to the next term. What is the derivative of x to the power 5? 5x to the 4. What is the factorial of 5? 5, 4, 3, 2, 1. Minus derivative of x to the 7, 7x to the 6. And that's 7, 6, 5, 4, 3, 2, 1. And let's stop there. Now I'm going to simplify. So I'll get cos of x is equal to 1 minus. Now let's have a look. 3x squared divided by 3 times 2 times 1. All the 3's are going to cancel. So I will get and obtain x squared, divide that by 2. Plus, oh sorry, this would be a plus 5x to the 4. The 5's will cancel. So I'll get x to the power 4. 4, 3, 2, 1 is 4 factorial. And then because I will maintain standard, I'll make that a 2 factorial. Let's go to the next one. The next term is x to the power 6. The 7's cancel. What am I left with? 6, 5, 4, which is 6 factorial. And of course, we know what the next term is. X to the power 8 over 8 factorial. And that generates, so differentiating sine x generates the series expansion for cos of x. So that is the usefulness of differentiation, where I can simply differentiate a particular function and generate another one, depending on the question. In other words, this can be used as a tool from now on. So let's complete the question. We need to find the cos of 3x. Well, the cos of 3x simply means wherever I see x in this series, I replace it by 3x. So let's do that. I get 1 minus. Now I'm just going to make this term a little easier. I hope you can see it as being easier. 1 over 2 factorial. And wherever I see x, what do I replace it with? 3x in brackets. And that must be all squared. Plus, I'll do the same here. I'll just separate the factorial notation. 3x all to the power 4. So every term is replaced by 3x. 1 over 8 factorial, 3x to the power 8. That will be a minus, alternating series. And then I can complete this by simplifying. What am I finally left with? 1. 3x all squared is 9x squared. Divide that by 2 factorial plus 3x to the power 4 over 4 factorial. What's 3 to the power 4? 81. X to the power 4 over 4 factorial. Where do I stop? They said the question states 4 non-zero terms. How many do I have so far? 1, 2, 3. So let's continue. Minus 3 to the power 3x to the power 6, 7, 2, 9, x to the power 6, divide that by 6 factorial. There's my 4 non-zero terms for cos 3x. So there we have a powerful tool that you can use with series. We can differentiate a series to generate another series or to simplify to answer a particular question. Okay, let's go on to the next example. Example 2, using the standard series for ln of 1 plus x, find a series expansion for 1 over 1 plus x up to the term containing x to the power 4. Now, if this is a question in a test or examination, they're specifically stating that we must use the standard series for ln of 1 plus x. So let's write down that standard series first. So what is the ln of 1 plus x? If you go to your list of standard series, that is x minus a half x squared plus 1 over 3 x cubed minus 1 over 4 x to the power 4 x to the power 5. Okay, just let me remove that. My eraser. I don't want that x there. So there is our standard series for ln of 1 plus x. Well, what is the question? They want a series expansion for 1 over 1 plus x. Well, how do I obtain that? Well, let's quickly recall. What is the derivative of ln of x? That is 1 over x. Therefore, what is the derivative of the ln of 1 plus x? Well, that derivative is 1 over 1 plus x. Now, I've written it like that specifically. Why? Simply for you to realize that the derivative of ln of 1 plus x is 1 over x, which answers the question of getting 1 over 1 plus x. But if I find the derivative of the left-hand side, I have to find the derivative of the entire right-hand side. So I'll have to find the derivative of the individual terms of the right-hand side. In other words, the derivative term by term. X to the power 5 minus, and that will give me derivative of x is 1. What is the derivative of a half x squared? X squared is 2x. My answer, x. You double check this. What is the derivative of x cubed? 3x squared. 3's cancel off. I'm left with x squared. I'm left with x to the power 3 plus x to the power 4 minus, and there we have generated a series expansion for 1 over 1 plus x simply by differentiating a previous known series. Now, do we only differentiate? No, we can also integrate. Let's look at example 1. Generate the series expansion for sine of x using the standard series of cos of x. Now, once again, the idea in this video is to equip you with a tool. And what is a tool? For you to realize that when you have a particular series, you can differentiate the series, you can integrate the series. So depending on the question, you may not have to use Maclaurin series. However, if they state you need to obtain a series expansion by first principles using the Maclaurin series, you got no option. But in this case, we can integrate. So let's consider the series for cos x. So in my solution, I have to use the standard series for cos x. What is my standard series for cos x? It's an even series. It's an alternating series. So it'll be 1 minus then plus 4 factorial x to the power 4 minus 1 over 1 over 6 factorial x to the power 6 plus, and so on. Therefore, to get sine x from cos x, what do? I can integrate. I can integrate both the left-hand side, so it will be the integral of cos x dx, but whatever I do on the left-hand side, I must do on the right-hand side. So I will integrate every single term. Plus 1 over 4 factorial minus 1 over 6 factorial x to the power 6 plus dx. Now we know what the integral of cos x. What is the integral of cos x? That is sine of x. Let's take each term individually. What is the integral of 1? That is x. What is the integral of x squared? Do you recall? Just a quick recap now. What is the integral of x squared dx? In differentiation, you subtract powers. In integration, you add powers. So you can add 1 and divide by that answer. So x squared, that's 2 plus 1 gives you 3, and divide by that. So in this case, let's take our answer. I'll leave 1 over 2 factorial. The derivative of x squared is x cubed over 3. We integrate term by term. This will be x to the power 5 over 5. Leave the factorial, 1 over 6 factorial, x to the power 7 over 7, and so on, plus my constant c. And now let's just simplify. I'll get sine of x is equal to, first term will be x minus x cubed divided by, well, let's have a look at 2 factorial times 3. 2 factorial multiplied by 3 is 2 times 1 times 3, just rearranging 3 times 2 times 1, which of course I can write as 3 factorial. So this fraction can be written as 3 factorial. And in a similar pattern, I can get x to the power 5 over 5 factorial minus x to the power 7 over 7 factorial, and there I have generated the sine series. How did I do that? By integration. Now you must say, well, you probably question, do we really need to know this? Oh, let's have a look at the next example. Find the integral of e to the x squared dx. Now, I'm pretty sure many of you are saying, well, oh, that's easy. Hey, let's just double check. We know that the integral of e to the x dx, what's the integral of e to the x dx? E to the x plus c. What is the integral of e to the 3x dx? That's e to the 3x, and we can compensate 1/3 plus, and you can double check by differentiation. But the moment you go to x squared, there is no way you can simply integrate e to the x squared unless you use u substitution. And if you do use u substitution, you have to check the derivative of x squared, and there's no other x in that integrand. In other words, you simply cannot integrate e to the x squared by all the methods that you know so far. Well, let's see. How can we go about integrating e to the x squared dx? Well, I will start off with e to the x, and there's my term, my series expansion for e to the x. And then using that series expansion, I will find a series expansion for e to the x squared. In other words, wherever I see x, what do I replace it with? X squared. So x is replaced by x squared. So let's do that. So this term, the 1 will stay. Then wherever I see x, what do I replace it by? X squared. Okay. Now I'm just going to separate the fraction, the denominator, and there's an x. Replace that x by x squared, and that will all be squared. So I'll do that in every single term. 1 over 3 factorial, x squared all cubed, 1 over 4 factorial, x squared, all to the power 4, and so on. And now I can simply multiply out and separate. X squared all squared gives me x to the power 4. 2 factorial is 2. X squared all cubed, x to the power 6. And I'm just going to work out what the value of 3 factorial is. 3 times 2 times 1, that's 6. I'll do the same in the last term. X to the power 8. 4 factorial is 24. But what am I asked to calculate? I'm asked to calculate the integral of e to the x squared. Therefore, the integral of the left-hand side is equal to the integral of the right-hand side. And all I have to do now is integrate term by term. Plus x to the power 8 over 24 plus integrate with respect to x dx. Now integrate each term. The integral of 1 is x plus. Okay, I do see your concern. I've left out the term x squared, so I'm just going to put that in. Let's just put it in a 1 plus x squared. And likewise over here, I'll get 1 plus x squared. Sorry about that. So integrating, let's just get my eraser. Let's remove that. Pen back. Okay, let's just recap. What was my mistake? I forgot to put in the x squared term. So I inserted the x squared term. So I must integrate all of the terms now. The integral of 1 is x. The integral of x cubed, we just did that. Add the 1 in the index and divide. Do likewise in the others. So here it will be x to the power 5, divide by 5, and of course there's still the 2. So it will be 2 times 5. Let's do the next one. Let's put the 6 down first. So it will be x to the power 7. Divide by 7. You got 24. X to the power 9. Divide by 9. Plus my constant c. And now let's just simplify. I'll get x plus x cubed over 3 plus x to the power 5 over 10, x to the power 7 over 42. And you can simplify the other terms as well. And there I have found a series expansion for the integral of e to the x. Now I want to go just one step further, and that is to find the actual value of a definite integral. So what do I mean by that? So here I have calculated the indefinite integral. Do you recall what the term indefinite means as far as integration is concerned? Simply the integral generating your particular answer. But what do I mean by a definite integral? Well, I'm going to use this particular example, and now I'm going to find the integral of e to the x squared dx. And the definite integral means that you must find a particular answer because you have a lower bound and an upper bound. So if that question is find the integral of e to the x squared from 0.2 to 0.9 dx, do you recall how to do that? Well, I hope you do, because all you have to do is substitute the upper bound and subtract the lower bound. In other words, the integral of e to the x squared, which we have just calculated, and there's the answer here. There's the answer. I substitute into that answer the upper bound. So wherever I see x, put 0.9. 0.9 cubed over 3. 0.9 to the power 5 over 10. 0.9 to the power 7 over 42. And then minus, now in the same terms, you substitute 0.2. So it will be subtract 0.2. 0.2 cubed over 3. 0.2 to the power 5 over 10. And then use your calculator, and I'd like you to double check this. I get a final answer of 1.01. You can check that. So there is your integration application to a power series. In other words, you can integrate a series. You can use series expansion as a tool to integrate a term which is difficult to integrate using your normal integration techniques. So just to recap on this one, this is the upper value or the upper bound that you've substituted minus the lower bound value of 0.2. Use your calculator to generate your final answer. Right, so at this stage we can say, yes, I can use differentiation and I can use integration as a tool to find terms that I cannot differentiate normally or I cannot integrate normally. Now we can look at the operations of series. What do I mean by operations? Very easy. How do you go about adding, subtracting series expansion? Now, I think that's going to be fairly straightforward. Your addition and subtraction of series is simply adding or subtracting like terms. For example, if I have to ask you, there's my two series that you see here. If I say, find a series expansion for e to the x plus sine of x. Now that's not going to be a problem. There's e to the x, there's sine of x, and I simply add the like terms. So 1 plus nothing, that will give me 1. There's an x, there's another x, x plus x will give you a 2x. Then I'll have to add plus x squared over 2 factorial. In other words, it's simple addition or subtraction of terms, of like terms. You simply have to write down the terms that there. And if they are like terms, you add them. So I'm just going to stop there because I don't think that's a difficult problem at all, hopefully. So where is there a problem? Well, yes. And that problem is in multiplication. But I'm hoping that this won't be a problem for you at all. So let's look at example 1. Find a series expansion for e to the x times sine of x. up to and including the term x to the power 4. Now that is extremely important. You'll see why. So how do I do it? Just like I add to series, like I've showed you there, I have to put the terms next to each other and add all the like terms. We do the same here. E to the x times sine of x. So it will be all the terms of e to the x multiplied by all the terms of sine of x. And how do you do that? Well, do you recall what to do in this case? X squared plus 2x minus 3 times, let's say, x plus 5. If you have to multiply, what do? You distribute x squared times x squared times 5, 2x times x, and so on. And that's exactly what you do in this multiplication. So you will take 1 and multiply 1 times x, 1 times, and so on. Every single one of these terms distributed into the second series. Is it low? Yes, it is. And that is why I emphasize, make sure you know where to stop. So we are going to stop by the term x to the power 4. And I'm simply going to write down the answers now. So let's distribute first the 1. 1 times x, that gives me x. 1 times 1 over 3 factorial x cubed is 1 over 3 factorial x cubed. 1 times 1 over 5 factorial, 1 over 5 factorial x to the power 5. But I'll stop there because they say I only need to go to x to the power 4. Okay, then the next one, maybe just to make sure you are following what I'm actually doing, let's just take this eraser, let's just remove all this. So the terms that I have so far are the terms that I use when I multiply by 1. Now I must take x. So let's multiply x times x. That's x squared. Then x times 1 over 3 factorial x to the power 3 is 1 over 3 factorial x to the power 4. And I won't go any further because I must stop at x to the power 4. So now that I've completed x, now I must do x squared. Now I must do x squared over 2 factorial. So let's do x squared over 2 factorial. X squared over 2 factorial times x. That will give me x cubed over 3 factorial. Once again, let's just erase that quickly. That's not 3 factorial. What is it? That's x squared over 2 factorial times x cubed over 2 factorial. Then, now let's look at the next one. X squared over 2 factorial multiplied by 1 over 3 factorial x cubed. So I'll get x to the power 5, and the factorial will be both 2 factorial times 3 factorial. Now I didn't need to do this particular term simply because it's x to the power 5. But the whole idea in this lesson is to equip you with the skill in doing this. So I'm going to stop there with x squared over 2 factorial. Now I'm going to take x cubed over 3 factorial and distribute that. So multiplying that by the first term x, I'll get x to the power 4 over 3 factorial. And I'll stop there because every other term after that will be a power greater than 4. And we only need to stop at the term x to the power 4. So now, looking for all the terms, add all the terms. X is all by itself. Is there x squared? There's the x squared. So it will be plus x squared. Where's the x cubes? There's the x cubed. There's the x cubed. Add those like terms. I'm going to get 4 over 6 x cubed. Where's the x to the power 4? There's x to the power 4. Here's another x to the power 4. Add those like terms and simplify. I get 1 over 3 x to the power 4. They didn't need x to the power 5, and I will stop right there. There's your series multiplication. So this is, let's just call this method 1. And this is a method that you've done at school, so there is no problem. However, there is slight confusion, as you have found out. When we do the multiplication, you can lose track very easily. There's also a method that we can use, and just something that you could possibly do if you want to. And you don't really need to do it, but if you would like to, you can follow a method that I have kind of suggested. Method 2. So let's look at this example. Determine a series expansion for e to the 2x times cos of x up to and including the term x to the power 4. So what I do is simply this. Remember, we need to get a series expansion. So I'm going to take 1 and multiply it. 1 times x squared. What I do is I take any of the terms, but I prefer the series expansion for e to the 2x, and I put all the terms of that series expansion, all the terms beneath each other here. 1, then 2x, then 2x squared, 4 over 3x cubed, and 2/3 x to the power 4 in a vertical column. And on the top, I indicate all the terms. Well, we could do this. Of any series expansion. In other words, a series expansion must contain a constant. It must contain a term with x. It must contain a term with x squared, with x cubed. So where do I stop? There you go. I will stop at the term containing x to the power 4. So how is this useful? Well, there, all you have to do is take the first term, 1, and multiply it into the corresponding other series. So multiply 1 times 1, 1 times 1. The answer is 1. That is a constant. Put it under the constant term there. So I'm putting all the answers for 1 in this row here. 1 times x squared minus x squared over 2 factorial is here. X squared over 2 factorial. Then 1 times x to the power 4 over 4 factorial is x to the power 4 over 4 factorial. 1 is now complete, but it's already in its correct term. Let's go to 2x now and do the same with 2x. 2x times 1, that gives you 2x. So now I must put them in this row. So this will be 2x. It may get a bit compact, but let's see. Then 2x times minus x squared over 2 factorial. that will give me minus 2x cubed over 2 factorial, and then 2x times x to the power 4 is x to the power 5. I don't need that term. So 2x is complete. And then I do the same for 2x squared, for x cubed, for x to the power 4, and I only go up to the terms with x to the power 4, and you can double check that. 2x squared times 2x squared times 1, that gives you 2x squared. I'll put that under the corresponding like term. Then 2 times minus, this will give me minus 2x to the power 4 over 2 factorial. Then go to x cubed. 4 over 3x cubed times the 1 will give me 4 over 3x cubed, and that will go in that row. Then 4 over 3 times x to the power 2 is x to the power 5. I don't need to do it. My highest power is x to the 4. Then go to 2/3 x to the 4th. 2/3 x to the 4th is 2/3 x to the power 4, and I will stop there. Why do I stop? Because any other term after that will give me a power greater than x to the power 4. Now what I'll do, I just take these all. Under each of these columns, you only see like terms, and so you simply add these like terms, 1 plus nothing else underneath, that gives you 1, then the 2x plus nothing else gives you plus 2x, and you can check the addition here. Over here I get 3 over 2 x squared, this instance 1 over 3 x cubed, and here I get 7 over 24 x to the power 4, and that is my series expansion for e to the 2x times cos of x. There you go. Now you can use either this method or the previous method of where you simply distribute, or you can find any other method that you wish. Most importantly, and I bring this to your attention, if you do get a question like this in examination or term or tests, I could ask you to give the coefficient. For example, here, what is the coefficient of x to the 4th? Or write down the first 3 terms of a series. So make sure you get the method, the process correct, and then you can answer any other terms after that. That brings this particular lesson to an end.